you'll recall the first exercise. I'll just run the whole thing real fast. The first exercise from this R script was we just tried to fit our data with polynomials of increasingly many terms. And the more terms you add, the better you're going to fit the data. But we realized that there's something not quite right about that because we're looking at the least squares quartic. It goes through every data point, but it absolutely is not going to be good for predicting other data points, or probably for estimating the coefficients of those terms, because it just looks awful. It looks horribly wrong. So we realized last time that it's not about fitting the data. If that's all you're doing, then you're going to lead yourself to fits that look crazy. So we decided that maybe there's more to it, and in fact the bias variance trade-off is what should guide our thinking in terms of picking a good curve to fit data, or a good surface maybe. So I described a few approaches to balancing bias and variance, and really what you're doing, the objective is to balance bias and variance, but kind of what you're doing is balancing misfit and complexity. So if you try not to use models that are more complex than you need, then that will help you avoid having too much variance in your procedure. If you try to use a model that fits the data well, that will tend to mean that you're using a model with low bias. So these sort of misfit and complexity quantities are sort of surrogates for bias and complexity, or I'm sorry, bias and variance. So anyway, another approach to balancing bias and variance was what I call iterative fitting. So the idea here is just keep fitting until the residuals look like noise. If the residuals look like noise, then you shouldn't continue trying to fit patterns. You should stop and say, okay, I've pulled out the pattern, and any more fitting than that might do more variance increasing than bias decreasing, and might result in a worse procedure. Well, okay, there's more to iterative fitting than that. It's also a greedy approach. So what did we do? We were looking at a data set called trees. We've got volume, girth, and height for every tree that was measured. And we said, okay, if I want to predict volume from girth and height, maybe if you're a logging company and you're trying to decide what trees to chop down, you could measure girth and height of the trees and estimate how much volume of timber you're going to get out of them without chopping them down. You can't really tell the volume of timber maybe until you've actually chopped the tree down and done something irreversible. But you can figure out girth and height without actually doing anything irreversible. So it's kind of it's a sensible idea to treat volume as a response and girth and height as explanatory. Girth and height are accessible to you before volume is. All right, so if I wanted to estimate volume from girth and height, what would I do? What approach would I take personally? That's what I'm describing here. I would plot each one. I would do the scatter plot of volume versus girth and volume versus height, and just figure out which one is more predictive. That would be my first step. Okay, looks like there's a positive relationship between x2 and y, but there's a very strong positive relationship between x1 and y. Really, the fact that it's positive doesn't matter. The question is, which which variable would you rather have? If you could only have one variable and you wanted to make your best guess of the y value, which variable would you rather have? And so the question is, which one of these uh, is more tightly, in which one of these plots do the points more tightly follow the curve? All right, so you've got a curve that relates y to x1 on average, and the points don't deviate too much from this curve relative to this. Here, okay, you've got a positive relationship, but if you knew the x value, there's still a huge amount of variation in what the y value could be. Here, if you knew the x value to be, 14, then you're looking at y values that are just, in this little band of reasonable possibilities for y. And that's true along the whole range pretty much. So the point is that x1 is better. X1 is more predictive. So I'm going to fit y using x1. Sorry. I'm going to fit y using x1. And I'm no longer going to require you to use the, at least for now, we're not going to bother with all of the matrix multiplication for coming up with the least squares coefficients. We'll use LM of y, simple linear model, y with x1. Draw the fit line. All right, so you can tell maybe, it looks pretty good, but you can kind of tell that at the edges, the points are above the least squares fit line, and in the middle, they're a little bit below. So I described this procedure that I like to do sometimes called the null lineup. Now, I probably wouldn't actually do that in this case. I would look at this plot and say, I probably wouldn't have even fit the line. I would have just said, there's too much of a curve. It's not super strong, but it's strong enough. I have enough experience looking at data to have an intuition for whether a curvature that I see is reasonably could reasonably be just noise, just due to random variation, versus being something that is a striking enough pattern that I don't think that it's just a matter of noise. I think there actually is a curvature to the relationship. So anyway, looking at this plot, I would have said that there's a curve, but for the sake of demonstration, let's pretend that I wasn't sure. Pretend that I'm considering saying maybe a line is a good enough way to fit the data, and maybe I'm even after looking at this, maybe I want to sort of determine whether that's a plausible, the residuals are plausibly just random noise. So I described this approach where I draw 8 plots that are random noise and one plot that is the residuals of this fit. So just to reiterate, we're trying to determine whether this line captures the pattern in this scatter plot. And if it does, then the residuals of the scatter plot should look like just random noise. There shouldn't be anything left to fit. There shouldn't be any pattern remaining in the residuals if we've captured all the pattern with our fit. So I'm going to draw those residuals. You can ask that question looking at this picture, but it's a lot easier just visually to try to answer that if instead you draw the residuals versus x1 instead of y versus x1, and you draw a nice horizontal dotted line. So I'm doing that, but I'm not just doing that once. I'm doing that with the true residuals from this plot, along with fake residuals that are just normal noise. 8 of these are fake residuals. 8 of these are noise plots, and one of these is the real plot. So I don't want to be fooled by randomness. I don't want to see a pattern that could easily just be due to normal noise. So I want to see if one of these stands out from the rest. If it does, then I can feel like there's something real in a real pattern remaining in the residuals, and that my initial fit, my line, didn't really capture the relationship. If none of these stand out, then I'm going to say, all right, it's reasonable that the true relationship is a line and the residuals are just normal noise. The residuals are just due to normal noise. All right, so the question is, does one of these stand out? And I guess this is a different batch of noise plots because I'm not setting the seed here. But if I look at these once again, I will kind of gravitate to this one and say there's a pretty strong curvature to the data here that none of the other plots really show anything quite as striking as this. Not to say that striking isn't necessarily the right word. This isn't super striking, but it stands out a bit. So then I ask, okay, which one of these is my real data? And I've got that saved as answer here. 3. Okay, so I look at 3, and that's the one that I said stands out a little bit more than the rest. So then I say, well, a line didn't fully capture the relationship. What was left was a curve. That's, just maybe it looks like a quadratic curve. So I'm going to say, well, maybe I should have used a quadratic instead in the first place. And if I had used that instead to fit the data, then here's what the least squares quadratic looks like. I can do the null lineup again. I don't think I'm actually gonna do that though, but it's the same process. You have residuals here, and the question is, do those residuals stand out from normal noise? And if they don't, then you can say, well, this is probably this is a reasonable guess for the true relationship. The true relationship is a quadratic, and the errors are normal noise kicking the true values off of the quadratic. So I'm not going to run that again for the sake of time. So now the question is, I've taken the first explanatory variable x1 into account. It was it had the strongest relationship, so I used it first. And I said, okay, well, we've got a quadratic function of x1. Now, what's left is x2. So it's the same reasoning. I say, can I predict the residuals using x2? Same reasoning that we used in determining whether or not the linear function of x1, or the line, the simple linear regression, was good enough. We looked at the residuals and said, is there a pattern remaining? And now we're going to do the same thing, but now we've got the residuals of our quadratic fit of x1, and the question is there a pattern remaining that the other explanatory variables can help us account for? Is there something left? Are these residuals predictable by the other explanatory variables? If they aren't, then that's an indication that you've gotten everything that you can. You're predicting the response about as well as you can based on the available information. But if one of the explanatory variables can predict the residuals, can help you predict the residuals, then you aren't using all of the available information. You aren't making the best possible predictions, because you could, for example, just take the first function into account, the quadratic for x1, and then calculate that to predict the y value, and then take whatever the x2 value is and predict the residual, and just add the residual prediction to the original prediction based on explanatory variable x1, and adding those together is going to give you a better overall prediction of y than you would have by just using x1. So that's the idea behind seeing if you can predict the residuals. If you could predict the residuals, then you could predict y better by just adding the fit of the residual versus x2. Although that's not actually how we're going to do it. We're going to go back and refit y. We're not going to just add the residuals. You can do that, but that's not actually optimal. All right, so is there a relationship remaining? Are the residuals predictable? We've got one explanatory variable remaining, so we just have to make that one scatter plot and say, are the residuals predictable? They are. There's an increasing relationship. The larger x2, the larger the residual tends to be. And this is another case where I would just use a line, probably, to fit this and be done with it. Because the relationship is so weak. I mean, there's definitely a true relationship, but it's so weak, so scattered. The data points are so scattered around that I can tell that I'm not going to want to use anything that's more complex than a line, because a line is going to capture the relationship about as well as possible, and I shouldn't feel confident about detecting some relationship that's more complex than that. But for the sake of demonstration, in this file, I did go ahead and do another null lineup and say, okay, so I fit the line. Do I think that the residuals of this have no pattern remaining? In other words, have I fully taken into account the relationship between these residuals and x2? So I drew these. I think for the sake of time, let's not actually spend time looking at these. But when I looked at these, my conclusion was that there's not a relationship remaining. None of these stands out in particular, and therefore I'm satisfied with my with the line as a reasonable fit for the relationship between the residuals and x2. So all right, I've got a linear function of x2, or let's say an affine function of x2, that I want to bring into the overall fit. So I'm going to go back and redo the least squares regression. I have x1 and x1 squared from the original step, and then I'm going to bring in x2, go back and fit all of those together. So at that point, once you've finished going through all your variables, you may end up with some terms that aren't necessarily important. And you may want to drop some terms out. So now this is actually, we're jumping the gun a little bit in covering this, because I'm looking at these significance probabilities, and these are coming from chapter 6 material. So you don't really need to know the details at this point of why these significance probabilities are what they are, but you can get the idea that they are significance probabilities of a test that the true coefficient corresponding to each row is actually 0. So if you believe that if the true coefficient were of x1 squared were actually 0, then the probability that the least squares coefficient of x1 squared would be at least as large as it is, or at least as far from 0 as it is on the order of 10 to the negative 6th. So we see some small significance probabilities, and that indicates that we're not really seeing strong evidence. I mean, this is 0.03. That's below 0.05. We don't really have good evidence that any of these terms are 0 and can be dropped. We may drop some eventually, because this is we're still going to check for interactions. You've got the intercept actually that has a large significance probability. Usually I don't really care if it's large or not. I don't really care if I'm keeping it or not. I mean, usually you may as well keep it. The intercept is not something that people really care about deciding whether to include or not include, or deciding whether it's actually 0 or not. Now, due to the nature of this data, I actually am going to decide later on to drop it. And that we'll think about what the variables mean and why that might lead me to drop the intercept. Usually we don't care about, we don't want to drop the intercept. We don't look at the significance probability and care about it. Okay, so there's an optional step here of checking for interactions. Well, there are all sorts of ways that your variables could interact. So we're not checking exhaustively. We're just going to try to look at products of our terms. And what does that look like in this case? Let's try to add an extra term that is a product of two terms. Well, two terms from the final fit that we ended up with at the end of step 1. We ended up with 3 terms: an x1, an x1 squared, and an x2. So what are the possible interaction terms here, or just possible product terms? You can multiply x1 by x1 squared, but that's just x1 cubed, and we've already ruled that out because we already fit x1 by itself, and we said x1 squared was fine. So we've already rejected x1 cubed. What else is there? There's x1, x2, and there's x1 squared x2. Now, I think I'm going to look at these significance probabilities in determining which one of those two interaction terms to think about first. So x1 doesn't seem to be nearly as important as x1 squared. Just looking at these significance probabilities, x1 is barely under 0.05. Now, okay, 0.05, I don't really care about 0.05. But the point is that the coefficient, the significance probability for x1 squared is orders of magnitude smaller than the significance probability of x1. So if one of these is more important than the other, it's x1 squared. x1 squared is the much more important term. Let's just bring it in first. So x1 squared times x2, that's going to be the first interaction term that we consider bringing into the model. So I'm adding that term to the model, x1 squared times x2. And I'm going to redo the fit. Oh, you know what? I'm missing a line. Summary of fit 6. So I brought in x1 squared x2, and suddenly nothing is significant. That's pretty strange. Or it seems pretty strange. Now this can happen because x1 squared x2 is actually pointing nearly in the same direction as x1 squared and or x2 and or x1. Well, more x1 squared and x2. And when you have explanatory variables that are sort of pointing in the same direction, you're going to tend to have larger, let's see, directions of small variance. You're going to tend to have variance inflation. Okay, this is another thing. I'm getting ahead of myself in this term too. I didn't want to wait any longer to do some more practical data analysis like this. So let's just say that your significance probabilities can appear to go down if you have explanatory variables that are pointing in basically the same direction. Then suddenly nothing is very significant anymore. Just imagine if you had 2 explanatory variables that were pointing in the exact same direction. You had 2 explanatory variables that were pointing in the exact same direction. You know, the only thing that differs is their length. Well, okay, so you want to try to figure out why why the y value is what it is, you literally can't tell if the y value is what it is because of the first explanatory variable or the second explanatory variable. If they're pointing in the exact same direction, it might be the case that one of those variables has a true coefficient of 0, and any pattern that you're seeing is due to the coefficient, a non-zero coefficient of explanatory variable 2, or it could be vice versa. It could be that explanatory variable 2 has actually no impact on y, and it's all due to explanatory variable 1. So the idea is you can't tell which variable matters if you have multiple variables pointing in almost the same direction. So the fact that these all skyrocketed means that the explanatory variables are all pointing in the same direction. It doesn't mean that none of them are important. It means that you can no longer tell which one is important or which ones are important. So sometimes when this happens, what I'll do is I'll go back and just try to add in terms one at a time from most important to least important, and just kind of see where I should stop and where, how many of these terms I need to add before I've um, one at a time, before adding another term doesn't really help. All right, so we're going to go way back, all the way back, and just redo the whole fit only using the most important term. The most important term is this interaction term, actually. That's unusual, but all right. Let's do that. Yes, this interaction term has an incredibly small significance probability. Now, what if I add back in x1? I'm not even going to define a fit. I'm just going to go ahead and call the summary of the LM object. What if I add in x1 to that? Does that help? No. According to significance probabilities, according to the significance probability, x1 isn't important once you've already taken x1 squared x2 into account. What about x1 squared? No. Oh, you know what? I'm missing something. 796. Okay, well, oh, I've got my parentheses in the wrong spot. So I forgot to use the I to protect that. All right, so I realized that I was seeing the same number. That was the exact same significance probability. So I forgot to use the I, which protects x1 squared. If you don't use the I, then it's going to do something. It's going to interpret what you're doing differently. I means square the x1 values, then use that as the explanatory variable, as the term. So okay, that x1 squared is not important. What about x2? If after I've already taken x1 squared x2 into account. What about x2? Is x2 important? No. No, according to significance probabilities, no. So once I've taken x1 squared x2 into account, nothing else really matters. This is the only term I need. And in fact, just for the heck of it, even we're looking and we're also seeing that the intercept doesn't matter. And I said we don't usually care about that. We don't usually want to drop the intercept term. But in this case, if you think about what the nature of the data is, we're trying to predict the height of the volume of timber that you would get from a tree given its girth and its height. So if the girth and the height of the tree are both 0, then okay, it would make sense that your volume would be exactly 0. So you can kind of think through that and say, well, dropping the intercept actually does make sense in this case. It is a logical thing to do, just based on the nature of the variables. So in this case, I will drop the intercept. So all I've got, all I've got here is y equals some coefficient times x1 squared x2. That's the entirety of my final fit, and we just came up with that from the steps of iterative fitting. Now I knew what I was hoping for in this case. So I wouldn't if I didn't know what the nature of the variables were, I wouldn't have necessarily gone exactly the route that I did uh, in this fitting procedure. But okay, let's see how well this does. Look at the r squared, 0.995. Just using this one term, x1 squared x2. So let's see. I'm going to plot the x1 squared x2 values versus y and just kind of see if maybe there's some other function of that would do even better. Maybe I could curve x1 squared x2 and do even better. Well, I don't think so. What's the line look like? Its intercept is 0. Its slope is the only coefficient that came out of our LM, out of our final LM function. There's the line. Now that's incredible. We only have one parameter, and we're predicting these y values beautifully. What do the residuals look like? I don't see an apparent pattern. You could say, well, maybe the data spreads out more over here than it does over here, but even that's a stretch. What do the residuals look like? They're pretty kind of normal. I mean, they're not highly skewed. You might say, oh, this looks highly skewed, but you could do a null lineup of box plots from normal draws with the sample size, and I don't think that this would seem more skewed. This wouldn't stand out in a lineup of box plots of normal draws of normal noise. So we can say, all right, well, we think that the true data generating mechanism is that, how about volume, the response, equals our coefficient of our final fit. The coefficient was right here in the LM output, LM summary, 0.002108 times girth squared times height. That was the only term that we ended up using, girth squared times height, plus some maybe normal, it's reasonable to think that the residuals look normal, then that would indicate that the errors are normal. And what's our estimate for the error variance? Well, you can calculate that. You can calculate your estimate according to the formula. We have a formula from chapter 4 for estimating the error variance. But it's actually also right here, residual standard error. It's called residual standard error. Actually, that's the standard deviation estimate. So it's the square root of the estimated error variance. So this is an estimate of the standard deviation of the normal errors that produced this data. All right, so volume equals 0.002108 times girth squared times height plus an error, and the error is normal with mean 0 and standard deviation 2.455. I just read it off from right there. This is an incredibly good function for mimicking this data. Fits the data well, and if you generate data according to this function, whoa, sticky keys. Shift key 5 times. Disable this keyboard shortcut. I don't know. I'll just close that. Did I mess something up? All right. So if you generate data according to this function, it's not going to be distinguishable basically from the data that we actually see. This line isn't this data set isn't going to stand out. In other words, this is a very good a very good guess for the data generating distribution for this data. All right, now let's think intuitively once again about the nature of the variables. Now we've got volume of timber, we've got girth, which is what the distance around, and we've got height. And if you think about the equation for volume of a cylinder, it's going to be something like girth squared, because girth is proportional to diameter or radius, proportional to radius, and you need the radius squared times height to get your volume. Your volume is proportional to radius squared times height, so it's also proportional to girth squared times height. So this just looking back and saying, okay, does this make sense? It's a very strange thing to end up with. Very strange to say, well, I had these two variables and I'm ending up fitting my response. I had these two explanatory variables and I'm ending up fitting my response as just some coefficient times the first variable squared times the second variable. That's odd. That's sort of unexpected. Generally, what you would do if you're just thinking in terms of multiple linear modeling, you're just going to predict volume as some coefficient times girth plus some coefficient times height. But if you're allowing for flexibility, if you're looking at plots and letting the data guide your choice of forms of functions, then you can end up with a volume equals some coefficient times the first, or let's say response equals some coefficient times the first variable squared times the second variable. You can end up with that if you're engaging with the data. If you're just doing multiple linear modeling without really making a lot of plots, without really thinking about what's going on, then you're not going to hit on this strange fit. Strange, I mean, I say strange because you wouldn't have guessed it. Now you would have guessed it based on knowing what these variables are, but if the variables weren't labeled, or if there's some other data set where you don't have, a very strong intuition for what the meanings of the variables are or what their relationships should be, then you wouldn't just come up with this. You wouldn't just come up with the first variable squared times second variable as your only term, unless you're doing something like iterative fitting, in my opinion. Now, okay, you could use some software that just tries a bunch of transformations of your variables instead of just using ordinary multiple linear regression, but I don't think that's as good. I like this procedure. This is exactly what I do. If I have a data set and I want to try to predict the response from the explanatory variables, and there are only, let's say 10 or fewer explanatory variables, then this is exactly what I'll do. I'll do one variable at a time. I'll look for sort of curvatures, and I'll look to try to capture relationships, and then I'll end up with a, sort of the simplest possible function that I can, for which the residuals aren't obviously predictable by the explanatory variables. All right, so that was a mouthful. Almost everyone is still here. I kind of was worried that, it's sort of hard to follow. It's a little hard to follow. I think you have to do it yourself. That's why the current homework is for you to do it yourself. All right, so I've got some simulated data. Let's see, do I still have Z read in? I hope so. Yeah, so I've got some simulated data that I've generated according to some function, and you're going to end up with some equation. You're going to end up with a statement like this. That is your guess about how I generated this data. All right, so it's going to be like mine, except this time you have 5 explanatory variables. And by the way, I didn't mention this in lecture 18.r, but it's a good idea often as your first step to just see if any of your variables are highly skewed. Now, none of the explanatory variables are, but actually the response variable is. This is insane. Look, you've got one giant 10 to the 40th. All right, you've got a bunch of tiny values. This is absurdly skewed data, and usually regression works best if your individual variables are reasonably normal. Someone suggest a transformation on this y that might make it more normal. What might I log? Good idea. This is really skewed. If you only have moderate skew, I mean, if the skew isn't too big, then you probably don't need to do anything. But if you have some skew that's not this crazy, then maybe a square root is worth trying. This is huge skew. If I take the log, now that's beautiful. Okay, so let's do log. You might even do z dollar log y is log of z dollar y. Okay, so treat z log y as your response for the iterative fitting procedure. Now, when you go back and you come up with a function, you go back and you come up with some sort of function relating. I want you to relate y to the explanatory variables. But for the iterative fitting part, try log y. Try predicting log y. If you can predict log y, then there's a natural way of predicting y by exponentiating that. All right, and so you're going to come up with a statement kind of like this. So was someone trying to ask a question about 2 minutes ago, and I may have cut you off?
Yeah, so I wanted to ask about the lecture 18 script, because once you add the interaction term and you see that everything else lost significance, I was
Yeah.
just wondering why you were like, instead of removing the interaction term, you were like, okay, then let's remove everything else.
Well, yes, that's a good question, but it's because I looked at, it wasn't really about removing everything else. It was about removing everything but the most important term. So if x1 had the smallest significance probability in this table, then I would have removed the interaction term and everything else and just gone with x1, and then added each one of these terms in turn to x1, to the x1 model, and seen which one helped most, if any did. So it was not about sort of saying, okay, this is the new thing, we're going to remove everything else. It was about looking at this table and saying everything lost its importance. Now, when that happens, I often will just say what's most important, and let's just rebuild from there and see if I see what matters. And maybe I would have ended up with, maybe what I would have ended up with is adding x1, or x1 squared, then x2, then x1, and then saying, well, I don't want to go back to all of these. That's what I don't want to build back all the way up to include all of these terms. But maybe if I would have added x1 and then, or x1 squared, and then add x1 if that's the next most significant. But the thing is, once I included the most significant term, and I tried adding each of the remaining terms, none of them mattered. None of them helped.
Yeah,
Professor
that makes
Brenda?
sense, I guess.
Yeah,
Sorry.
sorry, go ahead.
I guess it's just like my instinct would be kind of like, this was a fine model before we had interaction, so let's just undo that.
Yeah, that's reasonable. And I mean, frankly, I see step 3, I say optional. So I don't always even do this. I don't always even do the interactions. And I'm kind of making a point of doing them because I know that in this, this is I know what's supposed to happen for this data set just based on the nature of the variables. So I picked out this data set to show the potential of iterative fitting. If you really spend a lot of time and if you really, look for interactions, for example, then you can, it turns out, even without knowing what these variables are, volume, girth, and height, you could have done a procedure that that hit on, the exact right fit of how this data was generated. And the same thing is going to happen in the homework. So in the homework, there are going to be, I I believe there is an interaction. So it's optional. It says optional, but it is going to be play a role in the homework. Um, so yeah, I wouldn't necessarily, in general, I wouldn't necessarily bother with interactions, especially if you have lots of terms. Then there are a lot of different possibilities for what combinations to check. If you've kept 10 terms from your first step, then it may be quite a burden to check for interactions, and I might not even bother, just depending on sort of how much, whether it's worth the time and energy. Depends on what you're doing. But here there were only a few, and if there are only a few, I don't mind checking interactions. So yeah, so I added the interaction term and I said nothing matters. It's more about just noticing. It's more about noticing that the interaction was the most important thing here. Maybe you're right. If x1, x2, and if x1, x1 squared, and x2 all had lower significance probabilities, or if two or all of them had lower significance probabilities than the new term, then I would have said, okay, don't bother with the new term. That's just messing things up. It's about noticing that the new term turns out to be more important. Now that's very uncommon. So I would say this isn't typically what's going to happen. It's not typical that you're going to bring in an interaction term and it's going to be more important than the rest. And in that case, if it's not the most important one, or not even close to the most important one, then maybe don't bother. Don't bother pursuing it any further. You could try the other possible interaction term, which would have been x1, x2. It's just about noticing that this actually turned out to be the most important term. That was maybe a motivation for insisting on using it or trying to bring it into the model. All right, so what's the next question?
I had the same question, so thanks for answering.
All right, yeah.
I also had a really quick question. So I guess I am a little bit confused. Like, is it possible for you to make these I guess like the interactions, like can they be more than just like the two variables? Like if there were another variable, could you include that one as well? Like if there was like an x3?
And try all three of them multiplied together?
Yeah.
No, yeah, that's true. But even we're not even being exhaustive just by using products. So I certainly wouldn't bother with let's see, with quantitative explanatory variables. I don't think I would ever bother trying to take a product of three variables. I mean, you could do the interactions kind of iteratively, and you could sort of come up with a first layer of interactions and then try interactions of those, try products of those or something. And in that way, you could potentially get a cubic, but really that's getting to be, unless you have tons and tons of data, you're getting into a territory of just kind of doing things that are very complex and unlikely to be better than keeping it simple. And what I also said was, even just by using the product of x1 squared and x2, that's not really capturing every possible way that these functions could interact, that these variables could interact. It's possible that there's some term that is some function of x1 squared and times some other function of x2, or not even times, some other function of x1 squared and x2 that's not just the product, their product, that's, their, well, I don't want to even, it could be the exponential of their product or something, just, you can really kind of imagine terms that are really awkward. So we're not really trying everything. We're not being exhaustive. We're just seeing if there's a simple, this is kind of a simple way of seeing whether there's an obvious interaction term. You can't really, it's not feasible to check for everything. So this is just a first approximation, or this is just a simple way of trying to pull out a term that involves both x1 squared and x2. Trying to detect such a term. Now, okay, once you do this, and actually I did draw a scatter plot down here of x1 squared x2 to predict y. And it's possible that drawing that scatter plot could have indicated that it wasn't just x1 squared x2, it was some quadratic of x1 squared x2. I mean, that could have happened, and then you'd be just, instead you'd go back and you'd fit a quadratic of x1 squared x2, and then you would get, things can get very complicated. But it's unusual for that type of very complicated type of function to end up being helpful. So usually, here's my opinion with regard to iterative fitting. The naive thing to do when you're fitting is just to do multiple linear modeling. That's very common. Just do multiple linear modeling, and use the terms that are significant or something. Now that's very, very naive, because that's just using lines. Lines might not capture the relationship well. Now, you can go all out and try really complicated things. That's usually not going to be helpful either. But if you do iterative fitting and you do some just simple curves, usually something like a quadratic or a cubic can do a good job of kind of finding a local, capturing a relationship pretty well. Capturing the relationship as well as you plausibly can. So a multiple linear model, if I didn't draw the plots, I just did a multiple linear model, I'd have a line right here. And that's decent, but it really isn't capturing the relationship as well as possible. The relationship is captured better by a curve. It's more complex, but it's not just noise. It's more complex because it actually is doing better, convincingly better.